Welcome to our video lesson for section 2.2, Polynomials of High Degree. Today we're going to be discussing different functions and looking at their behaviors and some features that they might have. Let's get started. To begin with, we have our leading coefficient test. So to begin with, a polynomial is a function of the form a sub n x to the nth, a sub n minus 1, x to the nth minus 1, and it just keeps going. And what this is kind of showing us is we have several terms that are raised to some kind of power, but we're mostly concerned with our leading coefficient, which is going to be this first term. Okay, we do have this condition that n is going to be a non-negative integer. So we start with something like 0 or 1, 2, all the way down. But our leading coefficient is the important part because the leading coefficient is going to tell us what our degree is for the function. And that gives us a lot of information about it. All right, let's look at a couple of examples here. Our first example is a polynomial, negative 2x to the fifth plus 3x cubed minus 5x plus 1. All we want to do here is identify the leading coefficient and then use that to determine the degree of the polynomial. So our leading coefficient is always the value next to the variable with the highest exponent. In this case, we have our first term, negative 2x to the fifth, is going to give us that. The leading coefficient is a number, negative 2. And because we have an x to the fifth, the degree is going to be 5. Let's look at our next example. So again, we have a polynomial. It is x cubed plus 6x squared minus x plus 7. Conveniently, like the last example, this is already in descending order, so we can see that our first term is going to help us out. Our first term is x cubed, that is the highest power, so it's going to give us our leading coefficient. There's no value there, so we can assume that our leading coefficient is in fact a 1. And then the term is x cubed, so the degree is going to be 3. And for our final example here, we have just f of x equals 14. I'm going to go ahead and write something in here to help us identify our leading coefficient and our degree. I'm going to put x to the 0 power, because if you go back to our initial definition, we can have 0 as one of our terms, or sorry, as one of our powers. All right, since we only have one term here, our leading coefficient has to be 14. And then the degree for that is actually going to end up being 0. Once we identify the coefficient and the degree, we can use that information to determine a lot about the end behaviors of our function. So let's go ahead and look at how that works. All right, odd powers. So for odd power functions, as x moves without bound to the left or to the right, the graph is going to do a couple different things. So it's either going to rise or it's going to fall, depending on what side that we're on. Let's look at one specific situation. So when n is odd, and we have a leading coefficient that is positive, we can see two things that are happening. On the left side of our function, it is going down. On the right side, it is going up. So our leading coefficient is going to help us identify what's happening on the ends of our function, not so much on the insides. So we can say that on the right side, it's going to go up, and on the left side, it's definitely going to go down when we have a positive odd function. Let's compare this to a negative odd function. All right, so if n is actually, if n is odd and we have a negative coefficient, we can see we have a different behavior. It's going to actually go up on the left and it's going to go down on the right. So we can say that on the left side, it's going to go up, and on the right side, it's going to go down. Sometimes we also use the terms rise and fall. So just to reiterate here, if you have a positive odd, as we did with our first example over here, we can see it's going to go down on the left and up on the right. If you have a negative odd, then it's going to go up on the left and down on the right. All right, we're going to compare the odd powers to now the even powers. So for both of these examples, it's important to note that our n is going to be even, which means we have an even degree polynomial. If we have an even degree polynomial and our leading coefficient is positive, then what we're going to see is that it's going to rise on the left and the right. So it's going to go up on the left, and it's going to go up on the right as well. So one thing to note here for our even powers is it does the same thing on both sides, and if we contrast to the odd powers, it does the opposite. Let's look at our negative even power. So if our leading coefficient is in fact negative, and your n power is even, then on the left and the right, it's actually going to fall on both sides. So on the left, it's going to go down, and on the right, it's going to go down. So just to reiterate here, a positive even function is going to go up on both sides, and a negative even function is going to go down on both sides. Again, the positive or negative is based off the leading coefficient, and the even or odd is based off the degree of the function. All right, we're going to go ahead and apply this to this example here. We have three different polynomials here. We're going to identify the leading coefficient and then talk about the endpoint tendencies, so you can tell me if it's going up or down. For our first example, you can see that we have negative x cubed plus 4x. We want to identify the term that gives us the leading coefficient and the degree. In this case, it is your first term, negative x cubed. So I'm going to describe that. We have a negative x cubed, which means you have a negative function, and it's also an odd function. So we have a negative leading coefficient, we have an odd power, and so that tells me for sure that on the left side, it's going to go up, and on the right side, it's definitely going to go down. Those are the behaviors for all negative odd functions. Let's look at the second one. So we have x to the fourth minus 5x cubed plus 4. Again, you want to identify the term that gives you your leading coefficient and your degree. In this case, once again, because it's in descending order, it's our first term. Since there's no number in front, we can pretend like there's a 1 there, which is a positive value. So we have a positive function, and because the exponent is 4, we have an even degree. All right, since we have a positive even function, we can say that on the left side, it's going to go up, and on the right side, it's going to go up as well. All right, guys, your turn. For our third function, we have x to the fifth minus x. I want you to select from the options the correct answer for that one. All right, so to determine our answer, we want to find the term that gives us both our leading coefficient and our degree. Once again, it's our first term because it is in the correct order. We don't have a number there, so we can assume our coefficient is a 1, which means that we have a positive coefficient and our degree is going to be odd because our exponent is 5. Because we have a positive odd function, we know that on the left side it's going to go down, and on the right side it's going to go up. All right, we have a couple statements here that really mean the same thing, so we're going to kind of go through them and just clarify them. To begin with, a real number a is an x-intercept of a function y equals f of x if and only if f of a is equal to 0. So let's kind of break that down. What that's saying is if you plug in an x value into your function and your y value is 0, that means that you have an x-intercept. There's a couple different statements that really mean the same thing. So again, we have our function y equals f of x. If that is a polynomial function and we know that a is a real number, then the following statements are all the same. Statement number 1, we can see that if if x is equal to a, then a is a 0 of f. Okay. If x is equal to a, then a is a solution. So these are different names we can call them. We know that if the function equals 0, then a is a 0 of the function. We also can say if the function equals 0, then a is a solution of the function. And we know that we would get that solution by setting the entire function equal to 0. We can also say that x minus a is a factor of the polynomial. And last but not least, we can say that a comma 0 is an intercept. So just to kind of reiterate the things we can say here is if we know the function equals 0 for a specific x value, or we can call that a, then at that value we have a 0, we have a solution, we have a factor, and we have an x-intercept, all at that specific number. We're going to break this down and use it in a couple of examples following up. I know it's a little confusing to have this all kind of in one slide. So let's go ahead and take a look at how this applies to our examples. All right, so here's our example. We're going to try and break down all of those concepts. The question says, find all of the real zeros. All right, so let's talk about what the real zeros mean. We want to be able to find the zeros. That's what the question asks. But they could also be asked as finding the solutions, finding the factors, or finding the x-intercepts. And they all mean doing the exact same process. To begin with, what we're going to do is we're going to try and factor the function completely. And so what you can see we've done here is I took out the greatest common factor from both terms. So we take out a negative 2x squared, and then what I have left is an x squared minus 1. And then the x squared minus 1 I can factor again into an x minus 1 and an x plus 1. So I start off by finding all of my factors. Once you have found your factors, we want to then find the actual zeros. And the way that we find the zeros is by taking each one of our factors and setting them equal to 0. So if I set negative 2x squared equal to 0 and I solve for x, I get 0. If I set x minus 1 equal to 0 and I solve for x, I get 1. And if I set x plus 1 equal to 0 and I solve for x, I get x equal to negative 1. So I started off asking for all the real zeros. To find the real zeros, I factored. And then I found the solutions, which gave me the real zeros. And all of those solutions are going to be x-intercepts. And if you look at my graph, I can see my x-intercepts as 0, 0, -1, 0, and 1, 0. So this is an example of how they all kind of tie together. All right, we're going to apply that process here. Again, we have another example where we want to find all of the real zeros, which means we're going to factor, we're going to solve for our factors, and then we're also going to find our x-intercepts. All right, let's go ahead and try and factor. Similarly to our last example, we're going to start off by taking out the greatest common factor, which in this case is an x squared. And if I take out an x squared, then I have x squared minus x minus 2. I want to continue factoring my inside polynomial. So if I factor x squared minus x minus 2, then I get x minus 2 and x plus 1. All right, I want to make sure that I can find all of my x-intercepts, so I'm going to set this whole thing equal to 0. And I'm going to solve each one of these factors individually by setting them individually equal to 0. And if I do solve them all, then I get x equals 0, I get x equals 2, and I get x is equal to -1. So I have found all of my solutions. I have actually found all my real zeros already. And I'm going to convert them each into an x-intercept just so we can make that connection. So I have 0, 0, 2, 0, and I'm sorry, -1, 0. Then I can go ahead and plot all of my intercepts. And if I took this information and I paired it with my end behaviors, I could get a very rough sketch of my graph. So by looking at my leading coefficient, which in this case, we have x to the 4th, that is a positive even function, which means I know it's going to be going up on the left and up on the right. So if I go to sketch my function, I know that I have to have that feature. I know it has to be going up on both sides. And I'm just going to kind of connect the dots. Now again, this is a very rough sketch. It's not perfect. So I'm going to go down, come back up. I'm going to bounce off this, and we'll talk about why later. It's called a double root. And then I'm going to go up, and here we see a very rough sketch of a 4th power polynomial. And again, I accomplished that by finding my real zeros and by applying my endpoint behaviors. All right, one more example here. What I'd like you to do is go ahead and see if you can solve this on your own. Select the correct solutions, the correct zeros, which you're going to see pop up, and then come back and see how you did. All right, so just like other examples, we're going to start by taking out our greatest common factor, which is an x. So we have x times x to the 4th plus x squared minus 6. All right, now this one's a little bit more challenging because it's x to the 4th, not x squared, but we can factor the same way we would factor a quadratic. We just know we're going to have x squares as both of these. So I'm going to have x squared plus 3, and then x squared minus 2. All right, so I've completely factored it. From here, I want to go ahead and try and find the zeros. So what I'm going to do is set each factor equal to 0. And then I want to solve each one. This one is already solved. If I try and solve my second factor, the x squared plus 3, I get some imaginary numbers, which means I do not have a real 0 there. Key term, real 0. Finding imaginary values are solutions, but they're not real zeros. And then for my last one, if I solve for x, I'm going to get x is equal to plus or minus the square root of 2. All right, so those are all of our values. I could convert them all into intercepts. I would have 0, 0, radical 2, 0, and also negative radical 2 and 0. And I could plot those on my graph if I needed to. Square root of 2 is about 1.41, so we'd have a value here, and then the same for the -1. And then we'd have all of our information. All right, I alluded briefly to what we called a double root, and this kind of comes to our idea of multiplicity or repeating zeros. So for any polynomial function, if a factor of a minus x, the k value exists, and k is greater than 1, then we call that a repeating zero. And that happens at that value. Now there's two different behaviors here. If k is odd, then the graph is going to cross through at that value. So instead of touching it and bouncing off, as we saw in our example, it's going to cross through because we have an odd root. If instead k is even, the graph is going to touch but not cross through. It's going to bounce off at that value. So we're going to be identifying some of these, and I'll do a rough sketch of what it looks like on a graph. Again, if you have an odd power factor, then it's going to cross through the x-axis at your solution. If you have an even powered factor, then it's going to bounce off. Let's take a look at that. All right, so for our example here, we want to find a polynomial with the following things. We have a 0 at -1/2 with a multiplicity of 1. And I have a 0 at 3 with a multiplicity of 2. Before we find this polynomial, let's go ahead and sketch this out. So our 0 tells us where our x-intercept is going to be. The multiplicity tells us if it's going to cross through or bounce off of that value. So if I want to graph at -1/2, I can put a point there. And at 3, I can put a point there. So I have my x-intercepts graphed. And now I'm going to look at, do they cross through or do they bounce off? Since I have an odd multiplicity for -1/2, I know that at this value, we're going to be crossing through. I have an even value for my multiplicity with my value of 3, so it's going to bounce off. And what that means is when I go ahead and sketch this, I'm going to cross through here. When I get to 3, I'm going to bounce off and go back up. So that's a very rough sketch of what your function might look like, demonstrating your even and your odd multiplicities. But now I want to go ahead and find that actual equation. I'm going to go ahead and use my values to write my factors. So I have x minus the actual number, so minus a -1/2 with a multiplicity of 1. And then I have x minus 3 with a multiplicity of 2. All right, I can go ahead and say this is going to be plus 1/2. And I put the 1 at the very top there just to kind of get in the habit. The multiplicity applies directly to your exponent. So multiplicity of 1 means it's to the first power. Multiplicity of 2 means it's to the second power. I'm going to go ahead and square out our x minus 3 squared. And if I do, then we get x squared minus 6x plus 9. Bring down my x plus 1/2. And then my last assignment is to go ahead and distribute everything here. All right, so after we multiply and simplify everything, what we end up with as our final answer is x cubed minus 5.5x squared plus 6x plus 4.5. And if we look at our function and we try and analyze our behaviors, we can see we have a positive x cubed, so we're going down the left and up on the right. We have the appropriate x-intercepts, so our sketch here definitely matches up with what our function looks like. All right, guys, we're going to go ahead and attempt this again. We're going to do our sketch first, just kind of reiterate multiplicity. So we have the following zeros. We have 4, -3, 3, and 0. Apologize, there should be a comma separating these values here. I'm going to go ahead and put a dot for each one of my x-intercepts. So I know I have one at -3. I have one at +3. I have one at 4, and then I have one at 0. And each one has a multiplicity of 1, which means we're going to be crossing through, not bouncing off. So if I go ahead and do a rough sketch of this again, we're going to cross through, cross through, cross through, and then cross through. And again, we have a very rough sketch using multiplicity and our x-intercepts. We're going to verify this matches up with our endpoint behavior to make sure we did this correctly. All right, I'm going to go ahead and write down each one of our factors. So we have x minus 4, and then I have x minus a -3, x minus a +3, and then I'm going to put x minus 0 just to get into the habit. We'll simplify that, but make sure we do that correctly. And all of them have a multiplicity of 1, which applies directly to their exponent. So they're all raised to the first power. Again, just to be consistent with how we're doing this. All right, I'm going to simplify this, make it x plus 3. And I'm going to multiply some things together to make things a little easier using the idea of the difference of squares. We're going to multiply these together, and I'll multiply those together. So x minus 4 times x is going to yield x squared minus 4x. And then x plus 3 times x minus 3 is going to be x squared minus 9. And then I can go ahead and multiply all of that together. All right, after I multiply all of that and I simplify, I get x to the 4th minus 4x cubed minus 9x squared plus 36x. Again, we can kind of verify that our sketch and our final polynomial match up. I have a positive x to the 4th, which is a positive even function, so it's going to go up on both sides, and we can see it definitely is doing that. So our sketch and our graph match up. All right, here's our last example of trying to get a polynomial. We can see we have a couple zeros at 1. We have -3, 3, and 2/3 with multiplicity of 1. And then we have x equaling 0 with a multiplicity of 2. All right, let's go ahead and write our factors out. So we have x minus a -3, x minus 3, x minus 2/3, and then x minus 0 squared. The other ones do have multiplicity of 1, but we don't really have to write that. I'm going to go ahead and simplify this to be a plus. And now if you're like me, I don't really like fractions. I don't like that that's x minus 2/3. So something that we can do to make our life easier there is we can multiply the whole expression by our denominator of our fraction. So I can multiply each term by 3, and that'll help me get rid of my fraction and get some numbers that are easier to deal with. So what I now have is I have x plus 3, and then x minus 3, and then we have 3x minus 2, and finally x squared. Now while I did modify this, I'm not changing the solution of x equaling 2/3. I'm just kind of going backwards from simplifying to make it a little more complicated, but to get rid of my fraction as well. Okay, we can go ahead and multiply now, and similarly to the last example, I will multiply the first two expressions and the second two to get things going. If I multiply my first two expressions, we're going to go ahead and get x squared minus 9. If I multiply my second two expressions, then we get 3x to the third minus 2x squared. And now we got to go ahead and multiply all of that and then simplify our answer. All right, so what we end up getting as our final answer here is 3x to the fifth minus 2x to the fourth minus 27x cubed plus 18x squared. All right, guys, that's going to do it for our notes for this lesson. Go ahead and get started on homework. Good luck.